All right, welcome back, everybody. Today we are going to start chapter 2, and the cool thing is that immediately today you're going to recognize some of the stuff from chapter 1. We are going to be much more focused, like not as a class. I mean, we're getting here, but concept-wise, we're only looking at one specific thing. So over the next 7 sections, we will be focusing on chapter 2, and in chapter 2, it's all about quadratic functions, and equations. Okay, all of our focus is on quadratic functions and equations. Now, to start with, we are not going to begin with the type of quadratics that we saw in the bell ringer. We'll work up to them, but there's always a weird thing that happens when we graph quadratics. My guess is that last year or 2 years ago, whenever you took Algebra 1, you probably remember making an XY table eventually. But in 2.1, we're going to look at the nicest possible form of a quadratic. And hopefully that this doesn't have like trauma-inducing stuff, but we're going to be looking at transforming quadratics. Okay. Now, there are several forms that we could get a quadratic in, and we're going to deal with a really, really nice form of it today, which is different than the way I've taught it in the past, but I actually think that this is a much better sequence. Our first focus is just making sure that we all agree on what it means when we're talking about a quadratic function. So our bullet point is going to be a vocab today and a quadratic function. Okay, we all know that their graphs look like that thing. What else can you tell me? Can you write a general, like if I said write any quadratic function off to the side right now, could you? I think you probably would be able to, but if the language isn't there, we're not going to have it. What x to what power do you think makes it quadratic? Does anybody recall? A squared. The quadratics, you might hear them called the squaring functions as well. Because of that, there's a really easy way to define it. For a quadratic function to exist, all that we need is a function that can be written in a very particular form. Now, that form that we see for a quadratic is what we saw in the bell ringer, but it's not the only form. If it can be written like this, f of x, which this is just a function f with a variable x, that's all that means. If we can write it such that it's ax squared plus bx plus c, we have a quadratic. That's it. Now, there's only one little important caveat or restriction that we need to consider. Declan, if I let a be 0 and I just cover it up, is that a quadratic anymore?
No.
It kind of looks like mx plus b. I know the letters have changed, but that just looks like a straight line, just like we've been graphing in here. So the only requirement that we really need is to ensure that we have a quadratic, we're simply going to say a cannot be one particular number. What makes this not a quadratic anymore? What gets rid of the x squared? A cannot be 0. B can be 0, that's fine. C can be 0, also fine. But I wouldn't have a quadratic if a is 0, and only in that situation. Kian?
A could be like any number, right?
Any number, not 0. Yep, any number. Now, for these, when we look at graphing them, from this form, honestly, it kind of sucks. Now, it doesn't always suck, but there's a better way to graph these. So we have a quadratic function, and we're going to look at one very particular form of our quadratic function. And it is the nicest way to do this. We're going to define for ourselves what is called vertex form. Now, in the off chance that anybody moves tomorrow, I'm going to finish this vertex form of a quadratic. You can just write vertex form if it's clear we're talking about this. But if somebody were to move to a different school tomorrow, like out of the blue, you might see this referred to as vertex form. Other books, other teachers might call it graphing form. I prefer to call it standard form, but I'm at kind of odds with your textbook here. We're looking at vertex form. Now, we will sketch parabolas, and we're going to see it's really easy in this form, even though it's going to be ugly. For the definition of this guy, same thing. We're just going to use the same basic idea, but it's going to look a little different. A quadratic is in vertex form if it can be written or is written as follows. A And then in parentheses, we'll do x minus h squared plus k. This quadratic and this quadratic, they both produce the same type of graph, and we'll refine what that really looks like and such. This form is super duper nice. I'm going to add one more little thing to it. We're going to say where the point h comma k, whatever those numbers are, is the vertex. Okay. I have two questions. First, does this look kind of familiar to something we've already talked about this year?
Yeah.
Do you guys agree that this looks like all the same transformation stuff that we hit on and maybe you didn't fully grasp in chapter 1, but it looks pretty similar?
Yeah.
Okay. What's the vertex of a parabola or of a quadratic? All right, fancy language. Just a real quick check here. We're going to sketch a general, like without any numbers. We're going to see what this looks like and we're going to identify it, okay? Yes, ma'am.
Do you think that when we solve like the first problems or when you give us examples, you could do like a list of each step?
Yes, I'll do it off on the side. I'll change colors and I'll annotate much more clearly.
Okay.
Yep, absolutely. Thank you for asking. Okay, hypothetically, we're not graphing a problem here just so you know. I'm just going to sketch one. A parabola is just the shape of a quadratic. Most people think of it as a U, but it's not quite a U. When you draw a U, do you guys have it go like straight up and down? Like those lines go straight up when you draw it. Parabolas don't do this. They might look like they do it, but a parabola always comes out like this. Now it might get really, really steep, but it's never going to get perfectly vertical, which means no matter how far to the left I go, it keeps going. Like it looks like it's really steep over here, but if I went all the way over here, it'd just be really high, but it's still there. Okay, this is a parabola. I don't care if it opens up or down, doesn't matter, we'll talk about all that. But there is a minimum or a maximum value on this graph.
Maximum.
There's a maximum, you say. Where's the highest point? Like you might say here, but what does this arrow mean? It keeps going. Does it ever stop going up?
No.
So I don't think there's a maximum. Is there a smallest value on this purple
Yeah.
parabola?
Yeah.
Okay, you guys shout when it happens.
Ah!
Like here?
Hey.
Yeah, I love it. Okay, check it out. This right here is what we refer to as the vertex. That's it. When we talk about a parabola and its vertex, this is it. That lowest point, or if it opens like this, it's the highest point. Okay, for anything of this form, this point will always be h comma k. It is a piece of cake to solve. Now, there are other really handy key features of parabolas and quadratics that we'll graph out. When you guys, or that we'll work out, I'm sorry. When you learn to graph these, my guess is you use 3 or 5 points. Now, we're digging way back because it's been several years for some people, but we usually have the vertex in the middle, and then you would pick a point here, and then a point here, and then it's almost like they just reflect right over some line. 3 points eventually gives you 5, and if that doesn't make sense, we'll do a problem like this. This is our vertex. Okay, as we look at it, just a quick review. I should have formatted this differently because I wasn't expecting to draw it, so you might have to have longer lines. Just a quick reminder, what does this change in my graph? A, out in front of everything.
If it gets bigger, right? Or
Vertical, so stretch or compression. If it's stretched vertically, it's gotten thinner. Okay, now we didn't hit this super duper hard, but we're going to refine it right now. How do I tell based on the value of A if my graph gets thinner or wider? Notice I'm not asking about flipping upside down. Just if this is x squared, if I did 5x squared, does it get thinner or wider? So you gave me both. It's a good approach, but I'm not going to give you the shout out for it. Let's check real quick. Okay, here's x squared. Give me a number to put in front of it.
3.
Wider or thicker? What? Wider or thinner? I'm sorry.
Wider.
You say the blue one's?
The blue one up
The blue one's much thinner, right? It's been stretched vertically. That's it. So check it out. When we wrote this, I think people might have got confused. What do these symbols mean around this A?
absolute value.
Okay, so if A is greater than 1, it's a stretch. What if it's a compression? Absolute value of A is something else.
Greater than,
Less than 1. Okay, notice. This just tells me if it gets thinner or thicker. That's it. There's one more thing that this A value does. What if I make it negative? What changes? It's still thinner, but it's been reflected, right? So all we're going to do is, if we have absolute value here, we're also going to add reflect over x axis if A is negative. Now, we can write A is negative, but a more concise and shorter way is just less than 0. That means the same thing. Notice there's no absolute value here. So a negative 12x squared is super thin and reflected. A positive 1/2 is positive opening still, but much wider. Okay, what did H do? Horizontal translate. And I'm not going to put the rules here because these ones are a little bit easier, with the understanding that it's weird because it's backward in here, because it's already x minus h. Last one, what does K do? Vertical, up, down, left, up, down, not left. Cool. That was me, not you. Vertical translate. Now, in this form, I can't decide if I think, is this more intimidating or less intimidating than ax squared plus bx plus c?
More intimidating.
This is more intimidating. What's weird about it is it's so much easier to graph here. Because the hardest part of graphing a quadratic is deciding where your table needs to start. Always the hardest part. So let's just jump right in. We are going to graph one together. Before we jump in, anything that we spoke about here that already you guys said, oh, I don't like it, I don't get it. Okay, we'll know for sure after we try one. So here we go. I want us to make a table. Then we'll sketch it from our points that we get from our table. I also want us to identify or ID the vertex. We're going to find what is known as the axis of symmetry. Which, any suggestions for what or any guesses of what I use for my shorthand? Good call. It's AOS. Okay, so we're going to make a table. We're going to sketch it. We're going to find the vertex, the axis of symmetry, the extrema. I pronounce it extrema. I don't know why it came out weird just now. The domain and the range. Okay, lots of questions, but it all realistically just boils down to if we can make the table, the rest of it's super duper easy. Okay, so domain and range. Thank you for asking, y'all. Okay, so it looks like we're going to have time to start making our table is all. Let's knock one out. Let's say that we're going to try to graph from our first one 2, and then in parentheses we'll have x minus 3 squared plus 1. Okay, before we do anything else, can we identify, based on what we wrote above with the a times x minus h stuff, can you tell me what h and k are?
Yes. Yes.
What is h?
Negative.
So be really careful. I'm going to scroll up here. If it has to be x minus h, this is x minus,
Yes.
So 3.
it's 3. So check it out. This, my first step, if I'm looking at it, I would just write the vertex, because that's something we need, and we are going to use this. The vertex is at the point hk. That's what we have written above. And in this problem, h is 3. X minus 3. What's the k value?
1.
1. Check it out. We have our first little spot. Now, this is going to make it so easy. Have you guys picked up at all that I'm kind of a nerd?
Yes. A little.
Ow. Ow.
In a good way.
No. Okay. I think a nerd is a good thing, just for the record. Like, he'll never offend me. I'm okay with being a nerd. But I ain't no geek. All right. Looking at it. When I went to college, I went to the University of Wyoming. Is it 15?
Yeah.
Son of a bee. All right. We'll finish this tomorrow. Remind me about the story about the game. We're gonna play a game of squares tomorrow.
Okay.
You'll see. You're gonna hate it.
By the way, if you're dying to piglets, just wear anything gold and they won't attack you.